Hi, hello, good morning all. This is Dr. Abdul Pasha, Assistant Professor, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Here it is about the course called Power System Operation and Control. So in this course, the topic that is symmetrical lines. So what are symmetrical lines? How it will plays a key role in the power system network, that we will go to discuss in today's. So here coming to symmetric lines case, when the voltage magnitudes are at the two ends of the lines. For example, if you consider two lines, this is line 1, this is line 2. Voltage magnitudes V at the two ends of the line are equal. They are said to be equal. That means it is associated with sending end voltage and receiving end voltage. Receiving end voltage. So both are treating as same. That will be denoted with V, capital V. Then the line is said to be symmetrical in nature. Once again, how can we represent symmetrical lines? Means when the sending end voltage Vs and receiving end voltage Vr, both are said to be equal, then they are said to be symmetrical in nature. The lines are said to be symmetrical in nature. This condition must satisfy to obtain the symmetrical lines condition. So here, because power networks mostly operates as voltage sources, we will treat all the power networks as one of the voltage sources. The attempts are made to hold almost all node voltages. When it is acting as a power source, means they will treat all the node voltages at nearly rated values. Whatever the different combinations of the lines existing in the power system network, they will treat all the node voltages. So here node voltages means it may be V1, it may be V2, it may be V3. Like that, all the node voltages must be treated. So here, symmetric line therefore presents the realistic situation. Symmetric line will represent a realistic situation in the power system network. So coming to active and reactive powers of the transmission line, they are frequently normalized by selecting the surge impedance loading. When P and Q, active power means P, here Q means reactive power. For a transmission line, they are frequently normalized. How can we suppose it to normalize its real and reactive power coefficients? Means by one of the parameter called surge impedance loading, SIL. This will be treated as one of the base. Surge impedance loading is treated as one of the base. So it may suppose it to be defined as surge impedance loading is a measurement of real power. Usually we treat P, that is a real power, which are in megawatts. Real power which are in megawatts. That helps the system to operate to determine if a transmission line is acting as a capacitance or an inductance. Here the thing is that surge impedance loading will be treated as one of the measurement. That is for in terms of the real power coefficient, which will be expressed in megawatts. So here it helps to operate the determining the coefficient of transmission line. They will act as capacitance or inductance of the line. So here one more point we should treat is midpoint conditions of the symmetric line. So how we will treat midpoint conditions means magnitude of the midpoint voltage usually depends on the power transfer. So when you are treating midpoint of the line, they are supposed to treat the power transfer of the line. So this voltage particularly influence the line insulation, and also it needs to be well understood manner. That means for a symmetrical line where the end voltages are held at nominal values. So midpoint voltage shows that highest magnitude variation. Midpoint voltage shows highest magnitude variation. If it is in terms of the midpoint voltage, then it should be specified with a Vm. So receiving end voltage of symmetrical line is supposed to be expressed as Vr as Vm cos beta alpha by 2 minus Z naught Im sin beta alpha by 2. That is the one of the representation of the quotient for the receiving end voltage of the line. So here this equation determines the midpoint voltage of the symmetrical line, which will be as a function of power flow P on it. So practical considerations are most important in general. Their values of the line parameters and its C remains reasonably independent of the whole transmission voltage. So for example, typical values of I and C may lies in the particular ranges, which may be little bit variations from 0.1 less than or equals to 0.08 like that. So these are the variations we supposed to treat for the particular given system. So here L is the line inductance in kilometers. That should be 0.78 to 0.98, and its units are considered in millihenry per kilometer. Millihenry per kilometer. C is the line capacitance per kilometer. So its value is about 12.1 to 15.3 nanofarad per kilometer. So on the basis of these parameters, surge impedance Z0, that is treated as root LC. That should be lies in the range of 225 to 285. So when we make the case study of the line, to illustrate a number of important considerations, we should select 735 kV symmetrical losses transmission line with L as 0.932 millihenry per kilometer and the C as 12.2 nanofarad per kilometer. So with this line length is about 800 kilometer is considered. So with the values assigned to the particular line, the foregoing parameters are represented on the particular system. Here the reactive power balance at the receiving end is achieved with the sending end voltage Vs, and real power coefficient P is flowing from the sending end voltage to here, and the receiving end voltage is represented at an angle of minus delta. The opponent case will be achieved with the reactive power coefficient QC. So reactive power will become QR. With this, the line parameters are represented with P plus JQ. P plus JQ in terms of line. So this is the reactive power balance obtained at the receiving end case. So here it is important to calculate the required additional reactive power. This is to hold the entire receiving end voltage, that is about 1 per unit, and this will be implied to the 735 kV line. This is implied with the 735 kV line. Now here we should assume that it will be connected at the receiving end, means it is a load of fixed power factor. That will be 0.9 lagging in nature. So for any load condition, the reactive power balance at the receiving end is represented in the diagram. Then that reactive power is the QR plus QI combination, right? So where QR is the reactive power flow from the receiving end into the line, and this QI is the reactive power component of the load. So likewise we are going to represent, and QC is the reactive power needed from the system to hold a VR, that is to the rated value, which is about 1 per unit. So here we will represent the diagrammatic case. Here the reactive power flows at the receiving end. So from that analysis, this reactive power at the receiving end by P naught and QL by P naught and QC by P naught as a function of P by P naught is considered. So what happens means it is observed that at no load P becomes 0, that is nearly 1090 MVAR or 0.557 per unit. So reactive power must be absorbed to hold the receiving end voltage, that is about 1 per unit. So to avoid over insulating the line, so we must withstand over voltage under no load or light load conditions. A common practice is to be done to permanently connect the shunt reactors at both the ends to allow the line energization from the either ends of the line. So unfortunately, this natural protection becomes a liability under increase in load conditions. So this must be noted as we are operating symmetric lines. So for extra reactive power, QC is needed. This is to hold the terminal bus voltage at the desired level cases. So midpoint voltage of this line is calculated by considering one of the simple exercises, and the typical voltage distribution on the distribution line is going to be treated. So alternatively, there will be consideration of the receiving end of the line. So this is the diagram showing reactive power flows at the receiving end voltage. So this system is considered real power versus reactive power in per unit values. So real power as a P by P naught. Reactive power is Q in per unit. These real power coefficients are starting from 0, 0.2, 0.4, 0.6, 0.8, 1, 1.2, and the reactive power coefficients will be designed minus 0.2, minus 0.4, minus 0.6. And this is 0.2, 0.4, 0.6, 0.8, 1 to 1.2 we will consider. So here the line begins to start as a slope of the line as the reactive to real power coefficient. When it should exceeds to the line, then it will be reaching to the negative aspect, QC by P naught. Here this QR by P naught. The extent of the line will follows like this. So this will represent a typical voltage distribution on the particular distributed line. How it will be takes place means with respect to the voltage in per unit, the receiving end voltage becomes 1 to the 0.3, 0.6 P by P naught, and this will be 1 case and this will be 1.3 case. Like that, sending end voltage and receiving end voltage of the distribution will follows. So in this diagram, the load angle and the midpoint normalized per unit case voltage as a function of P by P naught per unit transfer on the line is going to be treated. So because of this line, it is observed that for light loading conditions below the surge impedance load case, midpoint voltage is going to be exceeds, and that is from nominal voltage to reach the highest value at no load condition. This is going to be treated mostly. So furthermore, for stability considerations, we should operate a load angle at an angle of 30 degrees, and it should be chosen to define the full load rating of the line, which is about 0.588 P naught. And midpoint voltage of the line will be 1.1058 per unit. So all the numerals are considered at a given angle for the whole system. So all these are expected at over voltages which should be lies in the range of 0.1 to 0.2 per unit value. These are from full load to no load, which are not within the acceptable limits. So therefore special techniques must be used to control these over voltages. So here is a consideration for midpoint voltage V and load angle, and which will be treated as a function of P by P naught. Then the graphical representation will follows, the curve will rises like this, and here voltage values are starting from 0 to 1.15. Slowly it should extend to the line 0.8 to 0.85, after that 0.9 and 0.95, 1, 1.05, 1.1 we are getting the maximum condition. This will be treating at 0.6, and this point will be achieved at 30 load angle in degrees, and this may extends from 0, 10, 20, 30 to up to 90 degrees. So load angle delta becomes 90 degrees considered, and a VM becomes treated at 1.15 case. So the real power ratio coefficients are ranging at 0 to 1.2, even though that it will be reaching to the maximum condition of the real power as 0.6. These are the conditions we must apply. So these expected overvoltage in the range from zero point 0.1 to zero point 0.2 per unit from full load to no load are not within the acceptable limits. So therefore special techniques are must be used to control the overvoltage. So there should be a very serious issue with the overvoltage. The loads may get damaged. Because of this unbalances in the voltage may causes fluctuations of the load. So it is possible to control the overall voltage profile of such lines, as that one described in this case will be studied by creating a midpoint voltage bus and connecting a controllable reactive power source. They will be called as VAR compensators, reactive volt amps compensators. So here it will represented by one of the surge impedance loading with the P naught. Then a reactive volt amps compensator absorbs reactive power, and above which it will supplies the reactive power phase. So a midpoint reactive volt amps compensator employed as a voltage controller, and the expected voltage profile will be at the along the line. So of course it is not important to hold the midpoint voltage, that will be at 1 per unit voltage, but especially if there is no load connected to it, also it is not necessary to have a controllable VAR source at the midpoint. So instead of that, adequately sized fixed or switched shunt reactors could be used to keep the voltage within the limits. So to continue this process with the aid of the case study, we should hold the midpoint voltage to the all load conditions by employing a continuous reactive controller of unlimited capacity. This must be treated while considering all these conditions. So here therefore the reactive volt amp requirement from the midpoint is with the controllers as QV, the QV as 2 QM. So in terms of the midpoint voltage, we can rewrite the power transfer of the line usually. So these are the angle characteristics representing. These are drawn real power P in megawatts versus load angle delta versus on the opponent side it will be reactive power quotient. This is in MVAR consideration. So the real power coefficients of the magnitude starting from the range 0, 500, 1000, 1500, instead of in terms of the 500 case, we will treat up to 4500 in megawatts. And here coming to the on another axis, delta will be treated up to 180 degrees. The Pmax will be 4500 megawatts and delta will be max up to 180 degrees and a reactive power coefficient up to 8000 max. So with respect to this maximum coefficients, by varying respective real power coefficients of the load angle, then we will get the curve like this. This is the reactive curve and the real power coefficient will be extending with the values. So the slope of the line will be representing with the delta angle as the source of power as this. So surge impedance loading is expected at the value of 2107.64. This is obtained at the surge impedance loading case about 1954. This is the surge impedance loading value. So with this value we can generate number of curves, these curves are with respect to the real reactive power coefficients, and they are supposed to be varied according to the variations in the load angle aspect, that is delta. So the lines which are meeting together at this point connecting to reactive power and load angle will be at 60 degrees with 433 value. So these coefficients will represent one of the symmetrical line angle characteristics. So here, as the conclusions will says that as the length of the line is increasing, so and so, this is the length of the line, as it increases on account of the line charging capacitances, line experiences significant overvoltage. This should be at light load conditions, and the overvoltage they can be limited by using fixed or switched shunt reactors. They treated at the lines of the end cases as well as their intermediate buses were supposed to be required. So the application of that midpoint or intermediate bus voltage, they will control the reactive volt compensators, will enhances the power transmission capacity of a given long line. So usually in practical cases, with the VAR controllers, they are sized by careful designing or selection of their continuous operating ranges. This is to hold the connecting bus voltages. They must be treated with the voltage at an acceptable range of values in the normal loading ranges. So active and passive VAR controllers, when they are fixed with the inductors or capacitors case, they are ready to employ to absorb or generate the reactive power constant. They constitutes the passive control case, and an active VAR control will, on the other hand, is produced when its reactive power is changed. So irrespective of the terminal voltage to which the reactive voltamps controllers are going to be connected into the system. So coming to the passive compensation of the network, so lossless line was analyzed for the passive compensation, and the case study is going to be presented will going to many numerical results. That means the problems associated with the voltage control, and they should need to exercise the reactive power control to make the system to be under working condition. So reactive power control for a line is often to be known as reactive power compensation. This methodology we already discussed and introduced so many methods for making reactive power compensation. We introduced so many methods, and some external devices or subsystems are also control the reactive power on the transmission line. They are known as compensators. The compensators will look into the consideration of cascaded connection of these inductors and capacitors. Based on that, we will treat line compensation on the line. Basically, they are treated at the line ends to treat for smooth conduction of the working output voltages. So a compensator mitigates the undesirable effects of the circuit parameters of the given line. So here some of the objectives of the line compensations are, they are invariably to increase the power transmission capacity of the line, and they are ready to keep the voltage profile of the line along its length within the acceptable bounds. This is to ensure the quality of the supply to the connected systems as well as to minimize the line insulation costs. So because of the reactive power compensation influences the power transmission capacity of the connected line, controlled compensation can be used. This is to improve the system stability by doing the maximum power transmission capacity, as well as it is ready to provide positive damping of the system. So like other systems, reactive power compensators are mostly dimensionized, and their types are selected on the basis of both their technical and cost effective cases. These are must treated under the influence of the symmetric lines. So this diagram will describes the two sections of a double circuit high voltage AC line for long distance transmission. So this may be considered with multiple sections, means the number of sections are designed here to consider with the high voltage AC line. This will be ready to take over along the long distance of the transmission network. Because of this, the voltage drops may be expected, and length of the line is continuously increasing, means loss coefficients are going to be there. So number of sections are dividing, means there has to make the maintenance of the whole double circuit network. So this will make over long distance of the entire line. So what are the effects on the power transfer capacity? Means the consideration of the series compensation is invariably raises the issue of its comparison. That means with the shunt compensation, this effect is more effective. So a simple system analysis can be performed to develop the basic understanding effect of the shunt and series compensation. This is based on the power transmission capacity. So based on the power transmission capacity, symmetrical lines will be derived. So here we will treat a short symmetrical electrical line. For an uncompensated line, we should treat Vs equals to Vr equals to V. Then power expressions becomes P equals to V square by XL sine delta. And if you treat this as sine delta as 2 sine delta by cos delta by 2, then we may treat voltage phasor expressions from IL becomes 2V by XL sine delta by 2. So these are the diagrams representing for the whole line when it is divided into subsections. Divided into two subsections. This is the sending end voltage V at an angle delta as XL by 2, XL by 2. This is Vm at an angle delta by 2. This is at the receiving end voltage at an angle 0. This is also at V at an angle 0 degrees. And Vs equals to V delta. Then delta becomes delta by 2. Then receiving end voltage becomes 0. Then the phasor sequence about JIL by XL. So as the sequence will follows, Vs equals to V delta when it reaches to J of IL plus delta L, XL plus delta X. So the delta coefficient may become split into two components, Vs and Vr, as sending end voltage and receiving end voltage. Sending end voltage is existing with an angle of delta, that is called power angle, and receiving end voltage which will be treated at an angle of 0 degrees. So because of these line constraints, the number of subsections are divided into equal number of phasor sequences as voltage and current phasor sequence. So the whole of the series compensation of the short symmetrical transmission line is going to be energized more according to the given power transferable capacity. So as we discussed in series compensation, if the effective reactance of the line is suitably controlled by inserting series capacitors, and if the line terminal voltages are held constant, then delta X will be in the line reactance will results to the delta L change. That will be in terms of the current of the line. Coming to the shunt compensation of the line, when you reconsider the short symmetrical line, then apply a shunt capacitor at the midpoint of the line so that shunt susceptance is added as delta BC. For the whole system, the power transfer in terms of the midpoint voltage on the line is going to be treated. So this is the diagram showing midpoint capacitor compensation of short symmetrical line, where sending end voltage is with a voltage of delta, and its series inductances are divided XL by 2, and there will be change in current with respect to the capacitor delta IC. They draw at an angle of delta by 2, then receiving end voltage will be obtained V at an angle 0 degrees. As the phasor is existing with receiving end voltage, the components are split into one of the Vm and delta IC by 2, and delta, this is IL, and delta by 2. So sending end voltage becomes V at an angle delta. So splitting coefficients are with Vm plus delta Vm. So all these are the coefficients which will be splitted according to the nature of the vector representation of the midpoint capacitor compensation of a simple short symmetrical line. So here reactive volts of the net rating of the series compensator is considered only at a value of 7.2%. This is required of the shunt compensator for the same changes in the power transfer case. So therefore, one must ensure that series capacitor compensation is not only achieved with the small MVR rating, but also it is automatically adjusted for the entire range of the line loading case. So, however, it will be the cost of the compensator. This is not directly related to the MVR rating, but coming to the series capacitor cost, it increases because they carry full line current and also their ends must be insulated for the whole line voltage piece. So, in practical applications of the series capacitors, it requires isolation and bypass arrangements of the capacitors, as they will be well designed protection and monitoring arrangements. So, for a complete discussion of series compensation, it will be recommended that readers will consult in the suitable conferences cases. So, these are some of the references whichever I have considered, and we can treat more number of lecture videos in the further cases.
Like, share, and subscribe. Hit the bell icon for more updates.